Hi everyone, thank you for coming. It's very pleasure to be here. I'm Kazuki Higashiguchi, a senior site reliability engineer at Autify. Autify is a startup company providing an AI-based no-code test automation platform for web applications and mobile applications. In this talk, I'm going to discuss lessons we got from project building and operating a stateful WebSocket server. In other words, this talk will provide you with general design consideration of stateful systems which maintain long living states. I'm going to talk about deployment first, then next observability. Let me touch on the background of this talk. Today's case study is an end-to-end test automation service for web applications. It allows customers to create tests, run tests against their application across browsers, and in parallel. Autify's infrastructure consists of 4 primary components. The bottom 2 are particularly relevant to this talk. And this stateful system component in this is last one, connect server. I'll explain these components by showing a diagram. The diagram shows the high-level infrastructure overview when a customer executes a test. A customer can trigger test executions using our management console. And then the web server requests the test connection of a worker. And the worker facilitates test execution and sends command to a device form. And the device sends a request to system under tests while it browses its application. When customers' applications are not accessible for the public internet, the connect server and client are added to the network load to execute tests. The responsibility is establishing a secure bidirectional tunnel connection with customers' private network. Technically, it uses WebSocket protocol for secure bidirectional tunnel connection, which is one of the typical stateful protocol. The connection lives for a long time until a customer disconnected. In addition, a connect server behaves as a proxy server. It accepts a proxy request from the device and transfers test connection to the target server over WebSocket connection. The key point in this talk is that connect server has 2 states, session and test connection. Now that I've finished sharing the context of this talk, so let's move on to the first point, robust deployment. As a background, we've been actively developing this application. Besides, high stability is required. Customers use this app service right now to test a test application on their private network. As a test automation platform, the stability of test execution is essential for our business. Considering these backgrounds, we should automate the process, and zero downtime deployment approach is preferred, since it is a mission-critical system component for customer test execution. A commonly used method for zero downtime deployment is blue-green deployment, as you know. Actually, we tried using a typical blue-green deployment approach, but it didn't work well to handle long-living states correctly. I'll demonstrate why it didn't work well. Let's say one client A, connects this stateful server, and one browser sends multiple requests over one session with client A. And in this situation, the server has one session as a state, and this session has some test connection as a child state. Next, we'll start preparing for a green environment. Once the deployment tool has been launched and tested new servers in the green environment, let's configure the router to forward new traffic to the green. And then it keeps the blue environment for a while in case we need to roll back in the blue environment. Still, a session with client A is alive, and some test executions are running. If we terminate the blue environment now, the browser gets network errors because ongoing test connections are closed unexpectedly. A customer will see the error page and feel uncomfortable with our product. It is a significant issue because we have to worry about critical failures every time we deploy changes. Let me discuss how to avoid these errors in deployment. In the last story, we found terminating the blue environment causes errors. That's because the servers are not ready to terminate if they are used for existing clients and test executions. Our solution for this situation is adding a verification step to confirm if the server in the blue environment is ready to terminate. It would be added before the step terminating the blue environment. The new step job checks the latest status until the blue environment is ready to terminate. To begin with, we should consider how to see the blue environment is ready to terminate. The options that come to mind would be the following: log monitoring and infrastructure metrics an option, but they are not perfect because they are not suitable for seeing application real-time status. In contrast, seeing internal states inside of the application is a good option because it's a single source of truth. But to adapt this idea, we need to consider our design to make stateful applications observable. There are two design tips to make internal states observable. The first tip is to implement an API to see metrics data of internal states. It is similar to the health endpoint pattern. It is a pattern to implement the API to telling the application's health. It makes it easy to understand the inner workings and system state by observing with external tools. For example, when one stateful server has 4 sessions and each session has several test connections, it will be a good idea to tell clients the number of running states. In doing this, the application must have a way to see the necessary details in each state to calculate the metrics data anytime. For example, we might need to store metadata of ongoing states in memory. Let's take a look at an example shown in the figure below. In this tracking design, if a new client starts a new session called session A, the application starts tracking in session A. And when your browser starts a test connection called test connection X, the application starts tracking this test connection. Then after finishing the life cycle of both states, the application deletes the tracking records. This design allows us to get meaningful information to see what's happening in the stateful system anytime. It should be considered at an earlier stage because this kind of mechanism might require us to redesign our application significantly if we work on its final stage. Thanks to this API, we can implement the steps to confirm if servers in the blue environment are ready to terminate. A custom step in the deployment pipeline first sends requests to get metrics of internal states. Once getting metrics, it determines if server is ready to terminate or not. And in our case, if the number of the session is 0, we can see the server is ready. Still, more is needed to address long-living states. Let's take a look at the happy path and unhappy path. A happy path is that every session a blue server shuts down when starting a deployment. The deployment tool finds a blue server is ready to terminate and terminates them. And deployment finishes successfully. On the other hand, this unhappy path happens more in the real world. Every session in a blue server keeps running. We waited for hours, but blue environment is not ready to terminate yet. At worst, we have to wait for existing sessions forever. This unhappy path indicates one issue with a stateful system that keeps states for a long time. The issue is that long-living existing sessions make the termination server in the blue environment wait for a long time. The reason is that each session keeps living until each client disconnects a WebSocket connection. In order to address this issue, A solution is to add a step to shut down idle sessions on servers in the blue environment. Let me explain it in details. The part consists of 4 steps. The first one is to get metrics of internal states using API. It is the same procedure as the last part. The second step is to determine if each server is idle. Unlike the last step, the part will focus on each session, each state of each server. Here, we implement the business logic to determine if each session is idle. If there is no test connection, the session is idle. And if else, there are any ongoing test connections. It is busy, and we must keep it up. The third step is to shut down idle sessions. One design tip of stateful system is implementing an API to control internal states. In our case, we implement the API endpoint to disconnect a session with a client. The fourth step is not about server application, but clients will reconnect to the green environment with router navigation. Note that client applications should be designed to reconnect on disconnection caused by deployment. By adding this new step, existing clients will be safely directed to the new server in the green environment in sequence. Deployment time has been mitigated because it is easier to find a safe time to disconnect on a per session basis than on per server basis. I am waiting for it. Okay. In order to implement this idea, we investigated some managed service, but they were not a fit. We use AWS to build our infrastructure. Therefore, we built our in-house deployment pipeline with AWS step functions and Lambda. Step functions allow us to create the automated visual workflow. It is a serverless approach and customizable. Of course, compared with using managed deployment services or tools, it would take time to build. Here is a built deployment pipeline with step function. As you can see, the outcome is a visual workflow, which is customized to achieve our requirements. The lesson here is that long-living states make it difficult to terminate an old server safely. Our approach is building a blue-green deployment pipeline with 2 steps controlling internal states. The first one was to shut down idle states, and second one was to verify blue servers are ready to terminate. In order to implement that, since an earlier stage, stateful applications should be designed to be observable and be able to control their internal states. This idea allows us to start with zero downtime deployment with a shorter deployment time. It took time to build a deployment pipeline, but I believe it makes sense to operate stateful systems. Moving on to the next topic, observability. I'm going to pick up 2 difficult questions to answer. The first question is, how can we see the actual usage of each stateful server? The cause of the difficulty is low visibility. Inside of applications, Inside of application is invisible from the external. But in stateful system, meaningful data is inside of the internal state of applications. In addition, these data are not stored persistently. One solution would be to create custom metrics visualizing the internal states. We can use the API mentioned earlier. Let's record metrics of internal states as a custom matrix. It allows us to visualize meaningful data inside of applications. For instance, we created a graph to show the trend of a number of test connections. The second question is, can you search all events and user requests related to a suspicious state? In stateful system, logic to handle internal state would be complex, and the core part of the application. Therefore, there would be chances to have something unknown around the stateful parts. However, it's difficult to search from each state without any considerations, because there is no searchable key by default. So I recommend you prepare searchable logs and traces with state identifiers. Assuming you did structured logging, I recommend adding an identifier of state to the key of log entries. Target logs are likely to be uniquely identifiable. In our case, when we want to investigate a session with a client, we can search for logs by the key of ID of sessions. When a test connection fails an unknown reason, we can search for logs by the ID of the test connection. Regarding traces, let me introduce our practice in an open source project, Selenium Grid4, which is an infrastructure component that makes it easy to run tests in parallel on multiple machines. It is instrumented with tracing using OpenTelemetry. A technique here is they add a state identifier into span attributes. It allows us to search for traces by helpful identifier. In Selenium, session ID is a unique identifier to handle a browser for testing. So it is used frequently when something unknown happens while handling a browser. A lesson here is to provide context into spans by adding an identifier of states as a span tag. The screenshot shows the actual trace of our system. You can see the trace has two identifiers pointing to the related internal states. Okay, let me conclude this chapter and the whole of my presentation. Building a robust deployment pipeline made us consider the observability of stateful system. That's why solutions for building a deployment can be used to make our stateful system observable. In addition, as internal states are the core part of a stateful system, I would recommend you improve metrics, logs, and traces around them. Well, that's it for me. Thank you so much for your attention.